Right, go on.
Hello, I'm Tom. I'm going to be talking about assembly and software reverse engineering. So, who am I? What are my credentials? Yeah, so WannaCry was a large ransomware attack in May 2017. It affected organizations such as the NHS, FedEx, and other big important things, and also little important things. And it affected a lot of things. This talk is going to be done from the perspective of, like, WannaCry has just happened, and we're going to try and use reverse engineering to try and figure out how to stop it. Originally, there was going to be a live demo when I did this talk in Cambridge, but I've got 15 minutes here, so there's not going to be time for that. So I don't know how this part's going to work, but, we'll see, I guess. We start with assembly. What is assembly? It consists of simple instructions. An instruction could literally just be moving information from, a register into a register, or between registers, or from, a register to memory. Registers are fixed-sized variables that exist within the CPU and can be accessed very quickly because they're within the CPU. However, due to the fact that they're fixed size and limited in number, things that don't fit have to go into memory. We'll go more into memory later on, and assembly runs line by line like anything else. So, there's supposed to be animations for each point to come up, but oh well. Memory is broken up into various segments in a program's memory. There's a text segment, which is the only executable segment in most programs, and it holds the code. There's a data segment, which holds variables, and part of the data segment is read-only data, which holds literals and constants. There's the heap, which contains dynamically allocated memory, and the stack, which is fairly important for this talk. It contains local variables and consists of these things called stack frames. So, how does a computer know which line we're on? You didn't ask, but I'm going to answer regardless. There are a number of special purpose registers, which are not used for the program's logic, but are used to kind of manage the program's execution. So that's the instruction pointer, which points at which instruction we're currently on. It will increment by 1 each time an instruction is executed, and can be manipulated by things like return and jump and stuff like that. There's a base and a stack pointer. I'll go more into this in another slide. But the base pointer points to the bottom of the stack, and the stack pointer points to the top of the stack, and that's how the program knows how big the stack is. And the base and the stack pointer are updated as we go into different functions as you create new stack frames. There's a flags register, which is fairly important too. It contains various important flags for program's execution, like the 0 flag, which tells you if the value of the previous operation is 0, which means that which could mean if you subtract two values from each other and the result is 0, the values are equal. So I touched on stack frames before. This was meant to come up one by one as well, but so stack frames are each time a function is called, a new stack frame is created, and that holds all the local variables and stuff for that function. However, it also holds the return address for the function, and it contains the parameters that were used when calling the function. So when the call instruction is run, you push the instruction pointer and the base pointer onto the stack, and then you set the stack pointer to be the base pointer, because the new base is the top of the previous stack frame. And then when you return, you pop the instruction pointer back into the instruction pointer, and the base pointer back into the base pointer, because the stack pointer should, by the end of the function, be back at the bottom of the stack frame. And so the base needs to return to where the previous base was. And this is when the stack frame gets destroyed. So when variables go out of scope, it's because by the end of the function, the stack frame is destroyed. This again will be important later on. So I don't know how this is going to work because it didn't work that well last time, but I'm going to do it anyways. I found this really cool thing called Godbolt, which compiles C into assembly, and you can see what lines of C look like in assembly. So does anyone have any suggestions for what to write and see, to see like what stuff compiles to? I'll
Hello World.
Sorry?
Hello World.
Hello World, okay. I can't actually see what I'm writing, by the way. So, did that work? No, import. You know, the reason this didn't work that well was because I couldn't see what I was doing as I was doing it. Yay, that did something. So, you can see at the start of the function, you push the instruction pointer and the base pointer and stuff. And then, I didn't add a return, but it automatically added a return because you're meant to return at the end of main. You can see the parameters are put into registers, and then the call instruction is run. The call instruction would then push the instruction pointer and the base pointer onto the stack and set the stack pointer to be the base pointer, and then change the instruction pointer to be where printf is. Printf then runs, and when printf finishes, it will return. The instruction pointer is set back to where it was before, so it will be on the next line after the call instruction. And the stack pointer, the base pointer is set back to the base pointer that was there before, which is all kept on the stack. So, does anyone else have anything they want me to write? Or attempt to write?
Some sort of fold.
Sorry? Oh, fold it. Yeah. Again, like I can't see what I'm doing, so. Oh, that was outside. Was that outside of me?
Yeah, outside of me, you make a push.
Oh, that's annoying. I'm going to move the big screen back to my own thing so I can actually see what I'm writing, and then. Yay, that seems to have worked.
Look at the screen. Yeah.
Sorry?
Look at the screen.
Oh, that's a good point, actually. Labels have been created, and as you iterate through the for loop, it'll compare the iterator to 10 in this case, and once it reaches that value, it'll jump out. The jump instruction, the jump instruction changes the instruction pointer to wherever the jump label is. So JLE jump less than will check that I can't see what pointer that is, but whatever register that is less than 9, and if so, it'll jump back to L3, wherever that is. Is that L3? Oh, anyways, yeah, you probably get the point. But yeah, so, and then I presume that pointer gets incremented by 1. Yeah, that's the add. So it'll increment it by 1, and whilst it's less than 9, it'll jump back, and once it's not less than 9, obviously, it'll fall through and complete the rest of the program. So, I think I should probably move on. So, I didn't know what image to put here, and me and my friends send this GIF to each other constantly, so I thought it'd be funny to put here as well. So how does this relate to stop being WannaCry? Compiled code can be converted to assembly because machine code and assembly have a one-to-one correlation. So what we could do is, we could try and figure out how the encryption happens, and if we can undo it. We can look at how it spreads and try to prevent it. We could try and write an antivirus signature for it. Or we could hope that the malware authors put a convenient kill switch that we could trigger. Normally in the live demo I'd actually do that, but then I don't have time for a live demo, so you're just going to have to deal with this. There was meant to be a slide here. I forgot it for the last presentation, and I seemingly forgot to add it for this one as well. Which was like explaining more about what reverse engineering is, but we're going straight into dynamic analysis, I guess. So, dynamic analysis tools, they let you run code line by line, and you can add breakpoints and stuff, like a debugger. In fact, GDB is really useful for dynamic analysis, because what you're able to do is you're able to look at registers and memory mid-execution, and if there's like a bit of assembly which you don't want to analyze or you don't really understand, you could see what happens when you run it, see the changes in the register values, and kind of infer what the code does from that. Yeah, you can look at memory areas such as the stack and the heap. But when you're analyzing malware, like WannaCry, you could accidentally encrypt your own files, which is less than ideal. So to kind of help with that, we have static analysis. With static analysis, we can look at function symbols, etc. quite nicely, and a lot of static analysis tools such as Ghidra have decompilers, which will turn assembly back into a C-like language. Sorry? Okay. So, yeah, there's cool control flow graphs which show you how the control flow of the program, and you can kind of... It's like trying to figure out what the code is doing using tools that analyze it without actually running the code, which is very useful when you're looking at malware because you don't want to accidentally run malware on your system. I would have used Ghidra to look at WannaCry and find the kill switch, but again, there's not time for that in this talk. And yeah, there's no risk of accidentally running malware on your system. This slide's shit because I couldn't be bothered anymore. So why is this useful? We can work out what software is doing. We can find difficult to find vulnerabilities, and we can modify what application behavior, which is known as patching. So patching, you can directly modify code without the source, so you can change individual instructions. So you could change a jump not equal to be a jump equal, and to skip stuff like authentication checks. Yeah, you can literally just change what the program does, which is very powerful, and is how a lot of piracy happens. Padding is a pain though, because instructions have to be aligned for the CPU to be able to execute them, and when you change them, it changes the padding, and you have to pad things to make them work. I'm going to go quickly because there's a minute left. Buffer overflows, prerequisite for ROP. A buffer overflow is when you have, on the stack, you might have a buffer of a certain number of bytes, and if you try to write more than that, you'll overflow and you'll overwrite other things on the stack. So remember that on the stack, there's data like the return pointer and the base pointer and parameters and stuff like that. So with return-oriented programming, it's super cool. And what you do is you change the return value so that when when you hit the ret instruction, it'll pop a value off the stack, but that stack will be a value which you've written yourself. and you can redirect it to any part of the code. Usually there'd be a couple lines of assembly you want to run, followed by another return instruction, which will then send you to somewhere else in the code, which you usually have kind of put in place. And you effectively get arbitrary code execution because you have a standard library in the text segment, which is the only part of memory which is executable. In the past, you were able to write shellcode on the stack and redirect execution to the stack, but because the stack is non-executable, you can no longer do that. So return-oriented programming is kind of a way of achieving arbitrary code execution whilst bypassing the non-executable stack. Yeah, that's the end, I guess. I'm not sure if there's time for questions, but if you have questions...